All right. Now that we've done a bit of a whirlwind tour of thermodynamics, we're really going to start with statistical mechanics in earnest. The first thing we're going to do, as I said last time, is we're going to talk about the microcanonical ensemble. Now, the examples I like to use are often from magnetism just because things end up being very well defined, but we're going to do other examples later. But we're going to start, as I said, with the microcanonical ensemble. And this is the situation where we know E, we know V, and we know N. And we're going to write down all microstates of the system and if you can actually do that, if you can do that in an efficient way, then you know everything. Then you can find any quantity you want, right? So let's consider our example is going to be 5 spin 1/2 particles on a line. They don't really have to be on a line, but the point is we can distinguish between the 5 particles, okay? And each can be up or down. Along some quantization axis, right? And then we're going to have some magnetic field parallel to the z direction, okay? Which means that each spin has energy plus mb or minus mb, and of course the situation is such that this is going to be anti-aligned with the field, so that would be spin down, and then this is going to be aligned with the field spin up. Okay, so the energy of the system is lowered if the particles have their spins aligned with the magnetic field. Now, there are 5 of these, so there are 2 to the 5 possible microstates, if I don't tell you anything else. All right, for 5 spins. But we can have an interesting constraint. Suppose total energy which is E of the whole system is minus mb, right? Where again I'm using, m here is magnetic moment of whatever our little spins are, okay? So this could be the Bohr magneton. I decided not to use mu just because we use mu for so many other things. Okay, so if this is our total energy, then not all of our 2 to the 5, not all of our 32 possible microstates are relevant anymore. For example, the state with everybody up not allowed, right? Because that would have an energy of plus 5 MB. So clearly this one is not okay. So now that we've said our total energy is minus MB, we can specify all the accessible microstates. So what are the accessible microstates? Well, clearly, if there's 5 spins and the net energy is minus MB, then this implies that there have to be 3 up spins and 2 down spins. So how many different ways are there to do that? We can have up, 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 down, down. That's one of them, right? But then we can sort of cyclically permute how we want to do this. So we can have up, up, down, down, up. We can have up, down, down, up, up. We can have down, down, up, up, up. I think you get the idea. So I've taken the liberty of writing down all the other possibilities, but these are the 10 microstates compatible with our constraint that E equals, the total energy equals minus mB. Okay, so our assumption of statistical mechanics, our fundamental assumption of statistical mechanics, is that if this is our constraint, then the system can be found with equal probability in any of these microstates. All of these microstates are compatible with our constraint, and we assume that these are all equally likely in the absence of any other knowledge. This is a very egalitarian, very democratic way to think about things, right? But if I tell you that these are the available pool of states, then that means we can, each one of these, the probability of being in any one of these states is 1/10, right? And that means we can find anything we want. So for example, we could find what is the average value of the, the magnetic moment, say, of spin 1, right? Well, that's going to be our magnitude m, and then we're going to have the sum of, I guess we could call it the state of spin 1, S1, times the probability of state I, and we're going to sum these over each of the states I, right? So there are 10 states, and so we can actually figure this out, right? We can actually do this for the states that I've enumerated up here. So we're going to have, each one of these has a probability of 1/10, so we're going to have 1/10 out in front, and then we're going to have m, right? And then what we're going to do is we're going to add, for each one of these states, we're going to have a 1 if the thing is up, and a -1 if the thing is down, and then we'll figure it if spin 1 is down, right? So we can easily see that we are going to have +1, +1, +1, -1. So let's basically do that. 1 + 1 + 1 -1. -1 +1 +1 -1. -1 +1 +1 -1. -1 -1 +1. -1 +1. And if I carefully add all of those together, what's my final result? I find we have 1, 2, 3, 2, 1, 3, excuse me, 1, 2, 3, -1, -1, +1, +1, +1. So this whole thing ends up giving me 2, which means our average value of spin 1 ends up equaling, of the magnetic moment of the first spin, ends up equaling m/5, right? If we wanted to, we could calculate far more complicated quantities. We could worry about we could worry about a whole bunch of different things, but we're not going to. But this is just our simple example showing you what happens in the microcanonical ensemble. Now recall, we had the idea we can do the canonical ensemble. I'm not going to redo it all, but we talked about this last week, right? Where if I've got a state that I can label with energy level E sub r, then the probability of the system being in that state is proportional to e to the minus beta E sub r, where beta is defined as 1/K Boltzmann temperature. Remember, in the canonical ensemble, my system is coupled to a bath, and it can exchange energy, so my system's total energy is not necessarily a constant thing. It's fluctuating all the time, but what you find is that there's a constant temperature if the thing's in equilibrium with a bath, right? So we did this argument based on omega, the number of states available to the bath, and we did that to derive this thing, which is sometimes called the Boltzmann factor. And with the Boltzmann factor, we were able to say, gee, even if we don't know what the coefficient of proportionality is here, we can define it. So we can basically say z, the partition function, is defined as the sum over all the possible microstates, e to the minus beta energy of each microstate, right? In which case, probability of being in a given microstate is e to the minus beta energy of that microstate over z. And I mentioned before, that means, for example, that if there is some quantity, I guess I didn't say exactly this, some quantity, maybe it's spin, I don't know, it's some other thing, but there's some quantity y that takes on value y sub r when microstate of the system is little r, then it just goes to reason that we can find that the average value of y in this canonical ensemble language is going to be the sum of y sub r, probability of being in state r, right? So what's that really going to look like? That's going to look like the sum of y sub r e to the minus beta e sub r all over z, right? And there you go. So, this is sort of how you generically can find averages of quantities in the canonical ensemble, and we're going to do something a little more definite in a moment. Now, the examples I worked through before, we did a single spin a half object, right, in some magnetic field along the quantization axis. And when we did that, we found, as we expected, that the partition function was e to the plus beta mb plus e to the minus beta mb. And we went from there, right? We were able to find the probability of the spin was up. We were able to find the probability that the spin was down. We were able to find the average magnetization, right? So the average magnetization, if you recall, was the probability that the thing was basically a plus m times the probability that the thing was in the upstate, e to the minus beta mb, right? And then a minus m times the probability that the particle was in the downstate, the anti-aligned state, right? And if we actually really look at this, this ends up looking like little m, our magnitude of the magnetic moment, hyperbolic tangent of beta mb. And we made this argument that if you can look at the situation in the large temperature limit, where the argument if the tanh is small and tanh x is approximately x, and you can get the Curie law, where you find that in the high temperature limit, the magnetic moment goes like 1 over the temperature, right? The second example, we did the so-called Schottky defect, which is really the same problem in disguise. It's a case of having a vacancy in a crystal, where if there's no vacancy, we set the energy to be 0. If there is a vacancy, we set the energy to be something like plus epsilon, and we were able to go and find the average energy of the system. We were able to go and find the specific heat, and the specific heat the heat capacity had some hump in it, and we called this is the Schottky peak in the heat capacity. So we mentioned that before. The example we did not do before that I can do a little bit now, consider this a tiny bit of a prelude before we do some stuff in more detail, before we really start talking, for example, about the ideal gas. We could talk about we're going to talk about the case of a single molecule, a single free molecule. Whoops. Sorry, my software was being a little difficult there because I was writing too high in the window. So, okay. So here we're going to talk about our things, our quantum numbers, if you will, our labels for how we distinguish different states are going to be the position and the momentum. So we can say the probability of finding our molecule in some little volume in position space d cubed r and some little volume in momentum space d cubed p, right? That's going to be proportional in some way to d cubed r, d cubed p, then the Boltzmann factor, e to the minus beta p squared over 2m, and of course here m is the mass of our particle, right? Now, what is the constant of proportionality? Actually, we can do a bit better than this. If we're talking about a probability here, this is the probability density, this is a probability in some region of phase space, then, in the end, the real probability, we're going to have to actually make it dimensionless, right? And so it turns out the thing that's actually going to save you, what you really want to do here is put 1 over Planck's constant cubed. It's not really terribly important right now, but this is going to end up being important later when we really want to do the serious treatment of the partition function for the ideal gas. All right. We're not going to do the full thing right now. We're going to do that soon. But there is one point that I want to show you. Well, actually, there are two things. First of all, we don't have to write in terms of momenta, right? We can talk about the probability, this is a different probability now, of my particle having a certain velocity in some little volume of velocity space. Well, that's going to be proportional, obviously, to that little volume of velocity space, but it's also going to be proportional, again, to the Boltzmann factor. But now we can write the Boltzmann factor in terms of the velocity. And so we're going to have e to the minus beta mv squared over 2, right? That makes sense. This is the thing that is going to end up giving us what's called the Maxwell-Boltzmann distribution, because usually when people talk about the Maxwell-Boltzmann distribution and they're worried about the kinetics of gases, the kinetic theory of gases, they care more about the speed or the velocity than they do the momentum. Okay, but really these two approaches are completely equivalent and interchangeable if you're careful about doing your variable changes. Now, the other point I want to make is we can add in gravity, right? If we want to add in gravity, and by this I mean an external gravitational field, an external gravitational potential, why would we do that? Well, just let's remember the system we're talking about here. We're talking about a single molecule that's free to move around. It's exchanging energy with some bath somehow in some unspecified way. Basically, you can imagine it's colliding with the walls of some chamber, and those walls are able to allow it to exchange energy with some reservoir that's at some finite known temperature, which is how we're getting our beta. So if we add in gravity, now we have the situation that the energy of the molecule, right, is going to be given not just by p squared over 2m, but it's going to be p squared over 2m plus mgz, right? This is some gravitational potential energy. Okay. So if we do that, what does it tell us? Well, we can look at our, for our caveat here, we've got the molecule, it's sitting at some known temperature, but it's interacting with the bath and so on to preserve that temperature. We can rewrite our expression for the probability. So now we have the probability of the thing being in some particular position with a certain momentum, right? Well, that's going to be proportional to everything we had before. We're going to have the d cubed r, the d cubed p, our little volume elements of position space and momentum space, which gives us phase space overall. I'm going to leave out the h here. It's kind of unimportant for what I'm trying to show you. But now we have e to the minus beta, the energy, which is going to basically be p squared over 2m plus mgz, right? That's the situation we have. So if we're, if basically all we care about is the probability of the thing being at some height, right? If that's all we care about, then we can integrate out, we can integrate out the other degrees of freedom, right? We can do our integral over the other position variables. We can do our integrals over momentum, right? So this probability of being at a certain height is going to be the integral dx dy. We're going to integrate out the spatial coordinate, the other spatial coordinates, and then we're going to have the integral over the momentum of our expression here, right? And so we're going to integrate out everything except the z coordinate, because the z coordinate shows up here. And so what you're going to find is that the probability of finding this particle that's in this gravitational potential in some at height z within some range plus or minus dz, basically, that's going to be proportional to, or when we do the integral, we're just going to get some numbers, right? So the residual remaining conditional probability is going to be proportional to e to the minus beta mgz dz, right? This is sometimes called the exponential atmosphere. So very crudely, it explains why the air gets thinner the higher up you go. Now, of course, the real atmosphere is not isothermal. It's not all sitting at the same temperature. We know it's colder when you get up high, at least over some range of heights. When you get up really high, way up into the upper reaches of the atmosphere, the temperatures go up again. But it's cold at the top of Mount Everest relative to the base. But the point is that it's really this exponential factor that really helps determine why air gets thin as you go up. Your air molecules have a certain amount, are sitting at some relatively well-defined temperature. They can exchange energy with their surroundings, and it's just less likely to find them up high, because finding them up high requires them to essentially have some of their energy be in the form of potential energy. All right? So why don't we pause there for a second while I get organized. All right. So a couple of other things here before we move on in detail doing other examples of the statistical mechanics. I do want to show you some relationships that have to be obeyed between different variables. I do also want to point out we could have a different constraint. And still use the canonical ensemble, right? So this is basically Rife section 6.4. If you're interested, you could basically say, here's my system, right? Here it is, and I could couple it to some reservoir. And you could ask yourself, we could basically dial the temperature of the reservoir up and down and ask, at what temperature does the system's energy stop changing, right? So this is basically like saying there is some total energy E, which is basically just shorthand for our average energy E, right? And we're going to adjust the temperature of the reservoir until this happens to equal the average that we would find from the canonical ensemble formalism here, right? So I guess my point is that if I told you the total energy, in principle, and you knew all the energy levels, right, and then in principle you could invert this relationship to find beta, right? You could figure out what temperature you're at, right? This is really annoying in practice, but you could do it. So I'm just throwing that out there. As I said, it's discussed in the book in section 6.4 if you care more about it. So building on what I just wrote, right, I just said that the average energy, no vector sign, the average energy, which really is this parameter we've been calling E the whole time, the average energy content of our system, you've already seen is going to be the sum of the energy of each microstate and then the probability of being in that microstate. Okay? Now, you can look at this and you can just see that, as I mentioned before, this is basically related to a derivative of log z, right? Because you can see for yourself that if I had, what this really is this is 1 over z, and then with a minus sign, partial z partial beta, right? Because when I take the derivative with respect to beta, every single term in my sum, I'm going to pull down an e sub r, and I'm going to have all of that show up just like the numerator. The 1 over z is from before. And so another way I could write this is that the average energy of my system is minus partial log z partial beta. So if I give you the microscopic energy levels of my system and I allow you to compute z, then I can find the average energy, right? And I mentioned to you before that F, the free energy, is minus k Boltzmann T natural log of z. And once you know F and E, and you know that F is also E minus TS, then you can rearrange things and you can solve for S. So at the end of some of this discussion, I'm going to actually summarize a whole bunch of thermodynamic relationships and how you can derive them from the partition function. I have kind of a little table that I've made that I actually got out of the book of Blundell that just summarizes all of these results, but you pretty much have everything you need right here. Now, the one thing I haven't talked about, right, is the pressure, and you kind of saw this a little bit on your homework problem. So the volume dependence, right? So remember, F is F of, T, V, and N are the natural variables for F, right? So where's the volume dependence come from? The volume dependence of Z comes from the energy levels. Right? It's easiest to visualize in the case of like a particle in a box or something, but clearly the size for the particle in the box, clearly the size of the box affects the energy levels themselves. So if you imagine some volume change and ask what does that do for us, right? So my change in the average energy is going to, what's going to happen here? Well, to first order, changes in the denominator aren't going to matter very much, so we're going to have 1 over z, and then we're going to have sum over r, the change of every energy level with the volume, right, times the volume change, and then, of course, we still have our e to the minus beta of each energy level, right? And so if you rewrite this again using derivatives of z, you're going to end up finding that the change in the energy ends up looking like minus 1 over z, 1 over beta partial z partial volume times the change in the volume, right? And we know that that's supposed to equal, if we really believe in thermo, that should equal minus P delta V, right? So then from there, we can find the pressure ends up looking like 1 over beta partial log Z partial volume. Now, again, you could have gotten that from our definitions of pressure in terms of the free energy, right? You would have gotten, you could have referred right back up to here and found that the pressure equals minus partial F partial volume at constant temperature, right? And that again is going to, from this definition of F, is going to give you the same answer for the pressure. So it's just another slightly different way of looking at it. Okay. Now let's build on what we've already had. So let me just restate this. The probability of the microstate R is 1 over Z e to the minus beta energy of that microstate. Okay. So we've said that the average energy is going to be the sum over the microstates, the energy of each microstate, and the probability of being in that microstate. That's fine. But now let's think a little bit about the general situation if we're going to have the energy change. And we're going to make another connection to thermodynamics, which will give us another way of thinking about stuff. Okay, so dE, how am I going to get changes in energy dE? Well, from this expression, and the product rule, right? We're going to have two ways to do this. We're going to have some terms that look like the energy levels are sitting still, and we're going to change the probability of being in each energy level. And then we're going to have a set of terms that are going to look like the energy levels themselves are going to change, but the probabilities aren't going to change, right? And if we're doing things in a quasi-static sort of process, kind of a nice, friendly adiabatic sort of thing where changing boundary conditions and stuff is not going to induce transitions between states, right? It's not that hard to identify this thing as the work part. This is how the energy changes with work. The answer is when you do work on a system, you change some macroscopic coordinate. If you're gentle about how you do it, you don't change the occupation of the energy levels, but you change what the energy levels themselves are doing, right? So I could have a situation where that's energy going that way, and here's a bunch of levels, and I can do some work on the system, or I can change some coordinate of the system, and after I've done that, my new energy levels might look like this now, right? But before, if I had a particle here and a particle here and maybe not a particle up there, and after I do this procedure, the particle here is still part there and the particle there is still there, this is when I'm doing work on the system. I'm not rearranging the populations, but I am changing what the energy levels themselves are doing. Now, the alternative to that is this term, and so you can probably guess how we should think about that term, right? This term has something to do with changes in energy due to heat, right? We're changing how the particle, how the relative occupations of the different microstates. The microstates themselves are sitting there, but we're changing how likely it is that they're occupied. And again, this kind of makes sense. If I've got a whole bunch of energy levels, here are a bunch of energy levels, and maybe my particles are hanging out in the lowest couple, and then I'm going to basically, if you imagine I'm going to add energy to the system in a disorganized way, what's that going to do? That's going to cause transitions from state to state, and I'm going to actually move particles around from my microstates that are going to be occupied. The probability of finding each microstate occupied is going to change. That's another way of saying that's the heat part. Okay, so just to repeat that, heat. Energy transferred versus heat changes the likelihood of relative microstate populations, but it doesn't change what the states are. Work actually changes something about the microstates so that their energy levels actually change. Okay? Now, one other comment. So if we take our definition of probability, right, I can rearrange this and I can solve for E sub r if I want to. And I'm going to write this in a certain way. I'm just going to say E sub r is going to be minus k Boltzmann t natural log of p sub r times z, right? That's all that really is just rearranging the terms in our definition of the probability, in our sort of partition functioning language for the probability of each microstate. All right. Now, S, okay, we already said that F equals E minus TS, which means that S is going to be E minus F over T, right? Makes sense? Yeah, I'm just rearranging the terms over here, right? So if I do that, if we plug that in, then what we're going to find is that S is going to look like K Boltzmann log Z minus the sum over the probabilities, the sum over the microstates, probability of each microstate, natural log Z times the probability of each microstate. Okay. And I can take my log of the product, which I got from here, right? I've got my log of the product, and because again, this bit comes from F, and this bit comes from E here. Okay, this bit here comes from E. I can split up this log, and I can move things around, right? So if I do that, I'm going to have K Boltzmann all out front of everything. That's going to give me the units I need. I'm going to have log Z, and then I'm going to have minus log Z times the sum of the probabilities. And then I'm going to have minus the sum of the probabilities log of the probabilities of each microstate. All right, so this thing here is just 1. The probabilities are properly normalized, which means that this term and this term cancel, and we are left with the entropy is going to be minus K Boltzmann, the sum over all the microstates, the probability of that microstate, natural log of the probability of that microstate. Now, this is a definition of entropy that is really useful if someone happens to tell you by some other means, here's the probability distribution of all the different microstates, find the entropy of the system. In statistical mechanics, there are times when that comes up. The other thing I should say is that this is where you get the tie to information theory. Now, I am no expert on this, but the point is that Claude Shannon, back in the 1940s and 50s, invented the modern theory of information, the modern theory of communications, and so this has to deal with signaling. And if you want to have, you want to worry about messages and how much information content they really have, right? You can talk about the entropy in some channel of communication, and that involves, if I've got a bunch of different possible configurations of my bits, say, in my digital signal, I can talk about how likely each configuration is, and then I can find the entropy that's contained in there. And what you find is that messages have low entropy and static has high entropy because all the different probable configurations of the bits are the same, right? So I just wanted to give you a heads up on this. I will try and dig up some good references for reading about information theory and how it connects to entropy. I will tell you that there are people out there in the high energy theory community who like to make extreme hay out of this concept and this idea that maybe there's some truly deep connection between the concept of entropy in terms of information and physical entropy, right? In fact, there are some who argue that maybe the entire universe in some sense is a statistical mechanical outgrowth of some underlying quantum states, where if you knew the microscopic degrees of freedom for the whole universe, for the actual fabric of space-time, you could actually go and do some statistical mechanics problem involving entropy, and out would fall things like general relativity, right? So there are people who talk about things like emergent, just to give you some buzzwords, emergent gravity. The person whose name is attached to that is Eric Verlinde. There are people who, the other really frustrating to me buzz phrase that shows up all the time is the idea of it from bit, which I think is too cutesy and twee to have any real physical meaning, but I don't always get a vote. So anyway, I will try and find you some references about information theory and how, if this is the sort of thing you're interested in, and I will try and add those to the course website. All right. So what are we going to do next? Well, before we move on completely from these standard partition functions, I just want to show you one more thing, right? What if we have a composite system? What do I mean by that? Well, I've got system A over here, right, and has energies, maybe E sub little a, we'll just label them that way, right? And then, for its microstates, which are labeled by little a, and then I've got the also creatively named system B, which has energies of its microstates see where I'm going with this, labeled by little b, E sub b, right? And you can ask what happens if I combine the two systems. Okay, so if, when I say combining the two systems, I'm not mucking about with the energies, right? So if the energies of the subsystems don't change, so what would be that be an example? What would be an example of that? That would be like I literally have, a box full of stuff in that system A, another box full of stuff in that system B, and I like to put the two of these things in a larger box, but not actually remove a partition between them. And now I have my larger box is the composite system, and so system A and system B remain whole, happy subsystems of their very own. We're just considering them all together, right? Well, what happens then? Well, the partition function of the composite system, what's that going to look like? Well, we're going to have to sum over all the microstates, little a and little b, of e to the minus beta energies of microstates of system A, if it's in that particular microstate, and then energy of system B, right, if it's in that particular microstate. And remember, the two systems are totally independent, right? So whether I'm in one particular microstate for system A or another particular microstate in system B doesn't really matter, right? This is, again, just saying that the energies of the subsystems don't care about each other. If this is the case, then, of course, I can separate this sum in the exponent into two exponents multiplied together, right? That's perfectly happy. And actually, if you go and you look and you sum over all possible A's and all possible B's, if you look term by term, what does that really look like? Well, this actually is the product of the two independent partition functions. This always struck me as a little non-obvious. I always had to kind of convince myself because I was never super comfortable with just eyeballing summations like that. But it turns out that this is actually fine. Okay, so what this means is that if I've got a composite system, then the product, the partition function of the composite system is the product of the partition function of the constituent systems. Now, we already knew that had to be the case, actually. I didn't emphasize this, but we know that the free energy is an extensive quantity, right? The Helmholtz free energy is an extensive thing. So if I have twice as much system, I should have twice as much Helmholtz free energy. We know that the Helmholtz free energy is proportional to log of z, right? So if I want to be able to add free energies when I extend my system, then my z's have to show up multiplied by each other inside that log in order for that to actually hold together. Okay? All right. All right. Now, for completeness, before we go and really do magnetism in more depth and talk about fluctuations and things, I do want to talk about the generalization of what we've been doing. Right? We're going to talk about the grand. I'm going to at least introduce, the grand canonical ensemble. So now we have our system, and it's talking to a reservoir, and we can exchange so the reservoir has energy. There's a total amount of energy E naught and a total amount of particles N naught. So now we're going to let the system in the reservoir actually exchange particles as well, right? So we had before, our system can have some energy, and we're going to have our reservoir, right, which I think I called bath. So we're going to have energy plus energy of the bath equals E naught, and we're going to have particle number of the reservoir plus particle number of the bath equals total particle number, right? And so just the argument that I made before last week, this idea that the probability of the system being in some microstate where the system has energy E sub r, and in this case, particle number N sub r, right? That's going to end up being proportional to, and again, we're assuming the reservoir is big, and so that these changes don't massively affect what's going on in the reservoir. That's the whole definition of reservoir. The probability of ending up in this situation is going to be proportional to the number of ways the bath can have energy E naught minus E sub r and particle number N naught minus N sub r, right? And so the same kind of arguments we did before, we're going to basically look at log omega b, and we're going to say that we're going to do our Taylor expansion of the log, right? But now we're not just going to expand in the energy, right? We're going to expand because we're going to assume omega b is highly peaked in some, very, very rapidly varying by many, many orders of magnitude. So this is going to approximately equal natural log of omega bath with all the energy and particles lying in there. And then we're going to have minus partial log omega bath, partial energy of the bath, E sub r, which is what we had before, and this is how we ended up deriving the Boltzmann factor. And now we're going to have another term. We're going to have minus partial log omega of the bath, partial n of the bath, n sub r, right? So these derivatives are evaluated at E naught and N naught, right? They're evaluated at these values of the energy and the value of the total number of particles, just because this is just a Taylor expansion. All right, so what are we going to do? Well, we're going to define beta of the bath. Like before, beta of the bath is defined as partial log omega of the bath, partial energy of the bath, evaluated at sort of that total condition. And now, so that's this guy. And now we're going to define one more term, alpha, right? And alpha is going to be defined as partial log omega of the bath, partial particle number of the bath. So how log of the number of microstates possible for the bath varies with changing the particle number, right? And then if we take these things and plug them in, we're going to end up finding that, and we do our exponentiations properly, that the probability of my system being in some microstate R that has energy E sub r and particle number N sub r, right, that's going to be proportional to e to the minus beta E sub r minus alpha N sub r. Okay, this is the grand canonical distribution, right? So this is a generalization of the Boltzmann factor that worries about particle number. Now, what we had before is that beta is defined as 1 over k Boltzmann t, right? So what's alpha? It turns out that alpha is defined as minus, let me make that more clear, minus the chemical potential for k Boltzmann t. Okay, so this is one way we define chemical potential. This is the way we define chemical potential. So now we have the grand partition function appears, right? So before we had regular z is just the sum over the microstates, e to the minus energy of each microstate. Well, now we're going to sum over not we're going to sum over the microstates, but including the particle number. So now we're going to have big old script z, right, is defined as sum over microstates, but now our microstates include different particle numbers, e to the minus beta energy of each microstate minus alpha particle number of each microstate. Okay? So this is our grand partition function, and we can do very similar things to what we did before. So what's the average energy of our system going to be, right? Which we're ordinarily going to ditch the overline. The average energy of our system that is in some sort of energetic and diffusive equilibrium with the reservoir, that's going to end up being 1 over big ol' script z, sum over r, the energy of each microstate, e to the minus beta energy of each microstate minus alpha, the particle number of each microstate. Okay, well, this is still minus 1 over z partial with respect to beta of, this time, big ol' script z, right? Because taking a derivative with respect to beta is still going to pull down minus the energy of each microstate from the sum in our definition. So this still works, right? So we could rewrite that as minus partial with respect to beta natural log of, in this case, the grand partition function. And we can do something similar for the particle number. Remember, the actual particle number isn't really fixed. The chemical potential is fixed to be of our system to be the same as that of the reservoir. So in the same way, in principle, we're going to drop the overline when we worry about it in the thermodynamic limit, but we can talk about how many particles are in our system. Well, what's that going to look like? That's going to look like 1 over big ol' script z, sum of each microstate, n sub r, e to the minus beta e sub r minus alpha n sub r, right? And I can look at that, and I can say that that is minus 1 over big ol' script z, partial big ol' script z, partial alpha, and that is, this is a constant beta, whereas this one is a constant alpha. Okay, partial with respect to alpha, and the other way I could write that is minus partial log big ol' script z, partial alpha. That's how I find the particle number. Now, we're going to come back to this later. We don't really use this again until we start talking about fermions and bosons, where it's really easy for us to do our sums over possible particle numbers in each state. In the case of fermions, my number of particles I can have in each microstate is going to be 0 or 1. And when it comes to bosons, my number of particles I can have in each microstate can be 0 up through infinity. And we're going to come back to this. All right, so when we really talk about Bose distributions and Fermi distributions, we will return to this grand canonical formalism. By the way, one thing I should just say, I mentioned this before, but instead of the analogy to what we had with the Helmholtz free energy, right, we now have the Landau free energy, which is a function of TV and chemical potential, and that is minus K Boltzmann T natural log of big ol' script z, the grand partition function. And this is completely analogous to the argument that we made before about the Helmholtz free energy being minus KT log regular partition function in the canonical ensemble. Now, I did want to say one more thing before I give you the big full-on table of statistical mechanics results and how they relate to thermodynamic quantities, right? I will give you that table. I will write it down for you, and you can look at it and copy it down. But before we do that, I did want to say something else, okay? So what I'm about to tell you is going to give us a nice interpretation, a different interpretation of heat capacities than what we had before. That's the direction we're trying to get to, right? So let's talk about fluctuations. So before, I just said, okay, here's my system, maybe in the grand, sorry, let's not even do it in the grand. Let's just do it in the canonical ensemble. Here's my system, and it's talking to some reservoir, and it's exchanging energy with the reservoir, so that this is described by some temperature T. All right. So the energy of the system is not, I should write that as system so you don't confuse that with entropy. The energy of the system is not exact, right? But it has a well-defined average given by what we've just written down before, right? So the average energy of the system, which usually we ditch the overline, which is a function of T, V, and N, right, is going to be minus partial log Z partial beta that we had before. Okay, so that's the average energy, right? And again, where did that come from? That came from basically taking 1 over Z sum of E sub R, e to the minus beta e sub r, right? That's where we got this. Okay, but now that we actually have the partition function, we can actually do better, we don't just have to find the average. We don't just have to find the average energy. We, if we wanted to, could find the square of the average of the squared energy, for example, and that means we can find the average of the mean square fluctuations in the energy, right? My system is sitting here. It's got some energy. That energy is actually bopping around all the time. It has some well-defined average as the system somehow, in some way, I have not specified. The magic word you're looking for is ergodicity. The system is busy exploring all possible microstates that are compatible with being at temperature T, but and at whatever volume it's at, right? So the energy is fluctuating, which means there's some average and there's mean square fluctuations about the average. Well, what's that going to be? What's this going to look like? The mean square deviations from the average. Well, that's, from our definitions from before, from early in the class, that's going to be the average of the square of the energy minus the square of the average, right? How do we find the average of this? So now we can actually compute these things. We have an expression for the average. Let's find an expression for the average of the square. So the square of the energy, what's that going to, the average of the square of the energy, what's that going to look like? Well, that's going to look like 1 over z, sum over the microstates, the square of the energy of each microstate times the probability of having that microstate, right? Okay. Well, again, how could I think about this? I could be one of these bloody-minded things where I can stare at it and say, wait, this is like taking 2 derivatives with respect to beta. It really is. One derivative with respect to beta pulls down a minus ER in the term. A second derivative with respect to beta pulls down another minus ER. The minus signs, the product of those is a plus sign, right? So I could write this, if I wanted to, as 1 over z, 2 derivatives with respect to beta of z, right? That's totally legit and mathematically okay. Now, I can do a little bit of calculus, right? I can again play games with the product rule for derivatives. And I can look at this, and I can say, you know what that really is? And this is the part where some people feel like I'm pulling a fast one, but I can say that's d by d beta of 1 over z partial beta, right, plus 1 over z squared partial z partial beta squared. That is formally true, right? If I took the derivative with respect to beta of this thing, I'm going to get something that looks like this, but I'm also going to get another term that is going to end up looking like that, right? It's going to end up looking like this term, okay? All right. So how should I really think about that? Let me just rewrite that. Okay. So just having rewritten that, this first term here is minus partial energy partial beta, partial average energy partial beta, right? This thing inside the parentheses that's the average energy. So minus the average energy. So that's what this first term is. And then the second term, you can pretty quickly realize that's already right there. That is the average energy squared. So this is very, very nice. We can easily write down then that the mean square fluctuations in the energy are just going to equal the average of the square minus the square of the average, and so that's just going to give me minus partial average energy partial beta, right? What is partial average energy partial beta? Well, we can go back and forth remembering that beta is 1 over k Boltzmann T, right? I can actually just do a little bit of a conversion here, right? And what you find actually is that CV, the heat capacity at constant volume, is minus 1 over k Boltzmann T squared partial energy partial beta, right? Because CV, at constant volume. Because remember, CV is partial energy, partial temperature at constant volume. And I can just use my algebraic and calculus skills to get this solution. So what we find then, right, is that the mean square fluctuations in the energy of my system are K Boltzmann T squared times the heat capacity at constant volume. That's pretty interesting, right? So systems that have a very, very large heat capacity tend to have bigger fluctuations in their energy content. That's an interesting thing. The other thing that is, this proves that CV must be positive. Well, at non-zero temperatures, CV has to be positive because it's the mean square of something, right? And the mean square of something is always going to be positive. So that's kind of cute. The bottom line here is it really just shows that there is a relationship, okay, between the fluctuations in some quantity, the energy in this case, and what you could call a susceptibility, how the energy changes with some sort of a stimulus, right? This is a generalized thing. This comes up again. We could do this in terms of magnetism, and what we would find would be that the magnetic susceptibility, which is how the magnetic moment changes with applied external field, is actually proportional to the fluctuations in the magnetization, the mean square fluctuations in the magnetization, right? Now, we could actually go and we could go just a tiny bit further with this particular result. One thing we could do is we say, okay, what is the square root, basically the standard error, if you will, the standard deviation in the energy, right? So that's the square root of the average of the mean square fluctuations divided by the energy itself. So this is how sharply is, if you want to, we can keep the overline in there. How sharply is the average energy defined, right? So how sharply is the average energy defined in the canonical ensemble as the system is busy exchanging energy with the bath? Well, let's do the ideal. Let's do an example. The monatomic ideal gas. I had told you that the energy is 3/2 nkt, right? We know that CV in that case is 3/2 nk Boltzmann. That's obvious. So we also have our definition from the previous slide of how we can find the mean square fluctuations. So if we plug all this in and work all this out, we end up with, in the numerator, we have a square root, right? And we have K Boltzmann T squared, and then we have CV. So we're going to have 3/2 nk Boltzmann in the numerator. And then in the denominator, we're going to have 3/2 nk Boltzmann, right? And so if we work all this out, this ends up being the square root of 2/3 times 1 over the square root of n, right? So the more particles I have, the smaller the fractional fluctuations in the energy content of my system. And this is sort of what we talked about a long time ago, that the bigger your thermodynamic system is, the fluctuations in your average quantities tend to go like 1 over square root of n. And this is actually a concrete example that shows that. So I know these videos are pretty dense, so I'm not actually going to take us all the way up to the 75-minute mark. I think instead I'm going to conclude this one with just the big old summary table that I'd mentioned before that really shows how you can get from things in the canonical ensemble which remember means there's some t, v, and n here, right, where we deal with the partition function. Okay, how are we going to get from statistical mechanics, where you're able to write down a partition function, to all the things you care about? So let me just summarize. All right, what did we learn? Well, we know the energy is minus d by d beta of log z. And we got that from our definition of what z looks like in terms of the energies of the microstates. I told you you can go and you can find that the Helmholtz free energy is minus k Boltzmann T log z, right? And of course the Helmholtz free energy is also E minus Ts, which means there's many different ways I can show this. I can find what S is, right? And again, this is S of T, V, and N in this case. That's going to equal, one way to get it is you can think of it as minus partial F partial T at constant volume, right? Or you could just write it as E minus F all over T. And like we said a couple of slides ago, that's going to be K Boltzmann T, excuse me, it's not K Boltzmann T, it's K Boltzmann log Z plus K Boltzmann T d log Z dt, where that derivative is a constant volume. Okay, so that's the entropy. We also said that the pressure is going to be minus partial the free energy, partial the volume at constant temperature. And again, from before, that's going to be K Boltzmann T partial log Z partial volume at constant temperature. All right. So we've got a couple of different ways of thinking about our fundamental thermodynamic potentials. We've got the Helmholtz free energy, we've got the entropy, we've got the energy. And of course, now that we have the pressure and we know the volume, if we wanted to, we can write the enthalpy, right? We can actually work in whatever variables we want. The enthalpy is going to be E plus PV. That's how we defined it, which means we can find the enthalpy from microscopics because we know what Z is. So that's going to end up equaling K Boltzmann T out front. And here we're going to have T partial log Z partial T at constant volume plus the volume times partial log V, partial log Z partial V at constant temperature, right? And you can see where we're just using our pressure result and plugging in here, and that's how we're getting this. Now we know H. We can find the Gibbs free energy if that floats our boat. So we can think of that as F plus PV, or we can think of it as H minus TS. They're completely equivalent things. And again, we can play games and actually do the plugging in, and that's going to give us K Boltzmann T minus log Z plus the volume that we had from up here, log Z partial volume at constant temperature, right? That's the Gibbs free energy. And then we can, like I said before, we have the heat capacity, which is partial energy, partial temperature at constant volume, but more usefully, more formally, it's T partial S partial T at constant volume. We have an expression for S up here, so we can go through and compute this either way. And when you do that, you're going to end up that the heat capacity is K Boltzmann T out front, and then 2 partial log Z partial temperature at constant volume plus T second derivative of log Z with respect to temperature at constant volume. There we go. And just to check the units, CV should have the same units as K Boltzmann, and there's a T out front, but there's a T in the denominator here from the derivative, and there's a net 1 over T in the second term from the denominator of the derivative as well. And so this does, in fact, have the correct units for CV. And as we showed before, CV has something to do, is proportional to the fluctuations in the energy about the average for our system. Okay, I know this is very formal. I know this was a lot of stuff, but there you go. You've now seen the kind of the full power of the canonical ensemble formalism with the partition function and all the things you can learn from it. And now, next time, what is next time? We're going to do magnetism, which is really, we're going to do a toy model of magnetism involving spins, but that's okay. And then the plan is to do something related to the ideal gas. And then following that, we're going to do the harmonic oscillator. right? These things are all very important classic examples, and they give you really some familiarity with how the formalism works. And this is how we start getting into all kinds of cool, neato, modern topics. Anyway, thanks. I hope that was useful for you. I know you probably are going to watch this at 2x anyway, but hopefully this was helpful to you, and I will see you all next time.